Here's the task I have for you. I'm giving you some data points. How would you fit a model that describes that data? Let's see how this problem appears and evolves at various stages of your education, from primary school all the way to becoming a postdoctoral researcher. Our journey begins in primary school. The powerful tool that you have available as a primary school student is a grid notebook. You can mark the two data points in Cartesian coordinates, and with the help of a ruler, you can easily draw a line that passes through those points. Your primary school linear model can even be used to extrapolate to new data points. Say your teacher asks you what is the value of y when x is equal to 7. You can count 7 squares along x, then follow the grid lines all the way to your line and count the number of squares along y. There's 4 of them, so the answer is 4. But what if your teacher challenges you and asks you, what is the value of y when x is equal to 2 3/7? First of all, there can be a lot of imprecision in where exactly does the 2 3/7 land in your grid notebook. But even if you were able to position 2 3/7 very well in your gridded Cartesian coordinates, there's some uncertainty about the y value. It seems to land sort of halfway between 2 and 3, but is 2.5 a correct answer? By the time you're in high school, you become comfortable with the general equation describing a line in Cartesian coordinates. You know that any possible line in the xy coordinates can be described by y equals ax plus b, where a and b are the free coefficients. All you need to do is to find the right a and b. Having the 2 points, 1, 2 and 4, 3, you can find a and b uniquely. You solve the system of 2 equations for the 2 unknowns a and b by plugging in the 2 data points. With some algebraic rearrangements, you get the final answer. A is 1/3 and b is 5/3. Here's the precise equation for your particular line. In fact, in high school, you become so comfortable dealing with algebraic expressions that you don't even need to draw your lines anymore. And now that you have the exact equation, there's no value of x that is a mystery to you. You can plug in even that nasty 2 3/7 to your equation to find that the corresponding y is equal to 2 10/21, almost 2.5. But here's the fun twist. What if I told you that the 2 points I gave you aren't the whole story? What if the 2 points come from a noisy measurement that collected a whole bunch of other data points, but not all of them fit onto the same line? It's enough to pick a pair of 2 other data points, and the line that passes through them is quite different from your earlier computation. So which line should you fit to your data points? Seems like your general equation for a line can't handle all of those points simultaneously, giving a different a and a different b each time you pick a new pair of points. So how do you decide on a single line? To make things even more interesting, what if a line isn't even the right trend for your noisy measurement? What if your data points look much more like they could be represented by a quadratic function? But even then, knowing the formula for the quadratic function with its 3 unknowns, a, b, and c, isn't exactly helpful. You seem to have many more data points than the 3 unknowns. Seems like we need extra tools to be able to tackle this problem. As an undergraduate student, you become familiar with the concept of regression. You learn that regression is the tool that will let you fit a function into your data. And that function doesn't even need to exactly pass through any of the data points, but still, in some sense, it will be the optimal way of fitting to your data. Even more so, as an undergrad, you're no longer preoccupied with thinking about single points in your dataset. Instead, you find that storing your data points as vectors or matrices is a much more powerful way of handling data. And once you do that, the rich world of linear algebra is available to you. You then learn that you can fit all sorts of interesting functional forms to your data that are linear combinations of some basis functions, phi. And you have a whole arsenal of basis functions at your disposal, from polynomials to trigonometric functions. Now you can impose an optimality condition for your data fit, and if you choose the mean squared error, you can solve the normal equations to determine the coefficients, W, of the linear combination of basis functions. All that you need there is to construct the matrix A that contains evaluations of your basis functions at your data points. If you'd like to learn more about the normal equations, you can check out the YouTube channel of my colleague in the video description. But here's the problem. What if the data points that I gave you have a very complicated shape in multiple dimensions, so that you're not even sure which basis functions to use? In graduate school, you're training to become a machine learning researcher. You learn about TensorFlow, a powerful library for solving many machine learning problems. You first decide to revisit that old high school problem, but this time solve it using gradient descent, a popular optimization algorithm that is at the core of many TensorFlow pipelines. You define your two data points, and you define your trainable parameters, A and B, which you initialize to ones. You then specify the gradient descent optimizer, and you solve the optimization problem over a number of iterations. In each optimization loop, you specify your linear model, where A and B are the trainable parameters. You compute the loss as the mean squared error, just like you did in your undergrad years. But this time, though, the optimizer is going to travel around the loss landscape and step by step get us closer to some local minimum at which the values of A and B are hopefully optimal. And to do so, you compute the partial derivatives of the loss with respect to each trainable parameter, A and B, and make tiny steps in the gradient direction. Throughout the optimization, you monitor the loss and terminate the computation once the loss is converged. Now you can recover the values of A and B from some converged iteration, which are indeed very close to the fractions 1/3 and 5/3 that you computed back in high school. Those two values correspond to the local minimum in the loss landscape. But let's not be silly. TensorFlow was created for much more than just helping you solve your high school homework. And this guy over here is really powerful. It records all operations done to trainable variables, theta, so that we can trace them back when computing the gradients. And no matter how convoluted those operations are, gradient tape keeps track of everything, so you can use very deep and highly nonlinear neural networks to fit your data. And with this, we've replaced the good old undergraduate basis functions with the power of automatic differentiation. And sure enough, we're able to fit all sorts of crazy functions into our complex data. But here's the thing. What if our data continually change in time so that its final distribution is not the one that we originally started with? How do we not only fit the model to data, but also let that model evolve as the data evolves? As a postdoctoral researcher, you no longer think of data as a collection of discrete points. Instead, you think of data as samples drawn from a certain probability distribution. There's a lot of comfort in hiding the data behind its distribution because it's a more compact way of describing your data. And if your data changes, no problem. You can model this by modeling the change in distribution. As long as you can trace the change in distribution, you can always generate new data samples. In fact, the capacity for data sampling coming from knowing the distribution is really powerful. And normalizing flows really take that generative potential to the next level. For a random variable y with a complex distribution, we can learn a function f theta that maps it to a variable with a very simple distribution, like a spherical Gaussian. And as long as f theta is a bijective function, we can invert this transformation. And we now generate a new data point x from the simple distribution and apply the inverted map to generate a sample from the distribution of y. In other words, we start with samples of x and samples of y and learn to transform y into x, which is called a normalizing direction. The function f theta essentially learns how to destroy information contained in y. But as long as f theta is invertible, we can reverse this process. The generative direction applied the inverse of f theta to the samples x. The function f theta can be a composition of many other invertible functions, allowing us to describe even very complicated data sets. Your postdoctoral training teaches you that there's both comfort and power in knowing the underlying data distribution. So that's the journey we've taken thus far. And what's coming next? Well, I don't know because I haven't been there yet, but I'll keep you posted once I get there. But the upshot of this story is that whether today you're here, or here, or here, or here, or even here, keep going, because with every step of the way, there are greater things waiting for you just around the corner. And the things that you thought were impossible just a while ago may be within your reach today because your toolbox has grown. And remember to sometimes take a pause and look back at the distance you've traveled thus far. There's peace and wisdom in realizing how much you've grown. And while you look back, if you see someone following behind you, make sure to give them a helping hand.